Hello, everyone. Welcome to STG216. My name is Delwyn Olivan. I'm a product manager on the Amazon EFS team. I'm joined by my colleagues, Ananth Vajanathan, who's another product manager on the EFS team, as well as Daryl Osborne, principal solution architect across file storage services. And we're really excited to talk to you today about file storage for builders and data scientists on Amazon EFS. But to start, wanted to first talk about the broad spectrum of file workloads that customers are running here on the AWS cloud. We're seeing customers of all different shapes and sizes, from storage and IT administrators to application owners, all the way to builders and data scientists on the other end of the spectrum. With this broad set of customer personas, we're also seeing a similarly large spectrum of workloads that they bring to the cloud. From enterprise IT applications and user shares to machine learning workloads and data and analytics applications, we're seeing customers bring all of them here to AWS. But with such a broad set of workloads, you might be wondering, how do we ensure that we can deliver the right solution for each of these, or the right solution across this spectrum? Well, when we talk to customers, there are really three different themes that emerge for why they're trying to run file storage or why they need file storage in the cloud. The first is that they're trying to deploy or migrate traditional network-attached storage or NAS solutions in the cloud so that they can increase agility and take advantage of new and innovative ways to process data on AWS. The second is that they're running what are called scale-out workloads, so compute-intensive workloads where they're really looking to take advantage of the cloud's virtually unlimited compute scale. And for these types of workloads, delivering fast and scalable storage is absolutely critical. And the third theme that we see is we see a lot of builders who are developing new cloud-native applications and workflows and that are looking for the easiest way to share data across cloud resources. So across compute, across containers, across serverless applications, and without any of the provisioning or planning that's typically required from storage solutions they've tried in the past. And so the way that we serve all the diverse workloads that we showed earlier is really starting by what the customer is trying to do and delivering a set of solutions that are purpose-built to address each of these three individual themes. So first, we have the Amazon FSx family of services, which deliver a selection of file systems that are designed to help customers who are building or running NAS workloads, as well as scale-out workloads here at AWS. Each individual FSx service is powered by a unique file system underneath that helps it address a different set or unique set of needs. With the broad spectrum of NAS workloads that we see, we actually have three individual FSx offerings to help customers with these types of applications. We offer FSx for Windows, FSx for NetApp ONTAP, and FSx for OpenZFS. For compute-intensive workloads, we offer a highly parallelized, high-performance file system called Amazon FSx for Lustre, which enables customers to run scale-out workloads and take advantage of the cloud's virtually unlimited scale. But of course, we're here to talk about EFS. EFS is designed and purpose-built for delivering the simplest solution for builders who are looking to share data across different cloud resources. So across traditional compute instances, across containers, across serverless functions. And EFS will be the focus of our session today. So if you're a builder or a data scientist looking to learn more about how you can deliver a simple, scalable solution for sharing data across compute resources, you're in the right place. So let's dive in. One of the big themes at this year's reInvent is putting your data to work. And there's no better example of putting your data to work than the workloads that builders and data scientists are bringing here to AWS. Everything from line of business applications to more data-intensive applications like machine learning workloads and data science and analytics, we're seeing builders bring more and more of these to AWS. But to run these workloads, builders actually need a simple way to share data across cloud resources. And that's where storage comes in. Storage is actually a critical enabler for these workloads, not just on the cloud, but anywhere you're trying to run them. Storage enables builders to unlock collaboration so that they can have teams of hundreds or thousands of artists and data scientists working on the same data set. Enables builders to unlock additional scale, so you can have thousands or tens of thousands of compute resources processing the same shared data. And lastly, enables builders to unlock higher levels of efficiency. It eliminates the need to duplicate data for every individual end user or every individual use case. So you only need to store that data once, and you can share it across all of your end users. But if storage is so critical, why does it still seem so hard? Many times we run into or we see builders that struggle with choosing or configuring the right storage solution for their workloads. And the short answer is, storage is hard. By show of hands, how many here in the audience know the difference between network-attached storage and a storage area network, for example? How many here know what types of storage capacity or performance their storage needs to deliver in terms of throughput, IOPS, latencies? How many of here know what application architecture, what architecture they're going to be using for their workloads in 10 years, in 15 years? So I didn't see too many hands, but it makes sense. Builders aren't storage experts, and you don't want to waste your time thinking about configuring or optimizing storage, because frankly, it gets in the way of what you do best, which is build. Builders are really looking for a solution that just works. But what does that mean? Well, first, you're looking for something that's configuration-free, so you don't have to worry about which knobs to turn or which settings you need to change to make storage work for your individual application. Second, you're looking for something that's fully elastic, so something that can scale up and down with your usage, so you don't need to think about provisioning infrastructure or resources to deliver the capacity or scale that you need. And third, you're looking for something that's accessible from anywhere, from any cloud resource, so you can always choose the right architecture for your application, whether it involves traditional server-based compute, containers, or serverless functions. And then lastly, you're looking for something that's cost optimized, something that doesn't require the effort that's typically needed to unlock these cost savings with traditional storage solutions. Well, luckily, Amazon EFS is designed to deliver exactly that experience. It's serverless, fully elastic, and built from the ground up to deliver a file storage solution that just works. But how does it address each of those four needs we mentioned? Well, first, Amazon EFS is configuration-free. But if you don't believe me, this is a screenshot of what the quick create option for EFS looks like in the AWS console. And as you can see here, all you need to do is give us a name, and even that's optional. And with the click of a button, you get a brand new, fully elastic, highly scalable file system. But what do you get when you click that button? Well, with one click, you get a highly secure, worry-free storage solution that's always there. Historically, you need a team of storage administrators to deliver all of these capabilities. But with EFS, you get all of this without having to think about it. You get storage that's highly available, so delivers 4 nines or 99.99% availability, with data that's automatically replicated across availability zones within an AWS region. You get high levels of durability. So it's designed for 11 nines of durability, so you don't need to worry about data loss, at least not in your lifetime or any lifetime of anyone you know. You get comprehensive security, which means you get automatic encryption at rest and at transit, and file system level permissions, and AWS security integrations that are necessary for building applications in a secure way on the cloud. And lastly, you get automatic performance. So Amazon EFS delivers levels of performance that are fit for a broad range of workloads. But on top of that automatic performance, builders and data scientists like yourselves automatically benefit from our continuing investments in raising the bar on that performance. Take latencies, for example, which are one of the 3 critical performance dimensions that matter for storage. At re:Invent last year, we were already delivering 1 millisecond latencies on reads and 2.8 millisecond latencies on writes for EFS one-zone file systems. At re:Invent this year, we're excited to announce that we've improved our latencies significantly on EFS. For reads, over the past year, we've reduced latencies by 75% from 1 millisecond down to 0.25 milliseconds. And on writes, we've reduced our latencies by 40% from 2.8 milliseconds down to 1.7 milliseconds. In fact, with the pace that we're innovating, over the past week since we've had to lock down these slides, we've actually reduced our write latencies even further down to 1.6 milliseconds. What does that mean for your workload? How does this translate? Well, if you take a couple of typical storage benchmarks as an example, like the time it takes to untar the latest Linux kernel, or how long it takes to run a simple hello world test on WordPress, these latency improvements translate to a 20 to 40% enhancement in terms of what you can deliver. I'll pass it off to my colleague Anand to talk about the other 3 needs and how EFS address them.
As a builder, that you're looking for is fully elastic storage without having to provision or plan for any of that infrastructure. So what does that mean? So EFS already provides fully elastic storage that can automatically scale up and down as your business needs it, and you only pay for the amount of storage that your file system consumes. In addition, an EFS file system scales to petabytes of data, so which means you can scale your file system to tens of petabytes of scale as needed. But what we also are excited to now announce is we are extending EFS's simplicity of storage to performance as well, so that you no longer have to provision or plan your performance. So let me take a pause here. I know we did a straw poll, and most of you said, you know, it's really hard to estimate or know your application's performance requirements, and that's really because performance planning is really, really hard, right? Especially when you build and deploy deploy applications at cloud scale. So when you're building a new application, you typically have to decide, you know, okay, or plan for performance, and so you have to decide on a level of throughput, for example, that your application might need. You might decide to be safe and provision throughput that's significantly higher than what your application might need. But then, as you can see in the second graph below, that means that you end up overpaying for all the time that your application isn't using the throughput, and so you're overpaying for your underutilized resources. On the other hand, if you have applications or workloads with unpredictable traffic, or if you have a new application, you might potentially set your throughput levels low, and so that may result in your application being throttled and providing your users with a bad experience, right? In both cases, you really don't want to be doing any of this, right? All you want is a simple solution that scales automatically without you having to provision or plan for any of this and removing all of the operational overhead. So, which is why we are super excited to announce Elastic Throughput, which we just recently launched, which completely eliminates all the provisioning and performance planning that you need to do, and you only pay for the throughput that you consume. So Elastic Throughput is a new throughput mode that provides your applications with as much throughput as they need, whenever they need it, and you only pay for what you use. It's great for new workloads where you don't know what the performance profile of those workloads are, or if you have spiky or unpredictable workloads that have performance requirements that are very difficult to forecast. A simple heuristic, for example, is looking at what your average to peak ratio or your peak to average ratio might be. So, for example, if you're looking at what the baseline throughput that your application is driving, versus what the peak throughput of what your application might be. So a number such as 5% makes sense in that you're driving your throughput on average only 5% of what it might, of what the peak should be, right? So that's maybe one way to think about when elastic throughput is a great fit for your application. So next, let's talk about accessibility and how EFS can be used across the various computing models that AWS provides. As builders, obviously, many of you are building net new applications on containers, or you're building serverless applications, or in some cases, even refactoring or re-architecting your applications from traditional EC2 to run on container-based services, right? And so you really want a file storage solution that can span all of these computing models. And that's where, again, EFS comes in. Because EFS is natively integrated with all of these compute models, and it's scalable. It can support tens of thousands of EC2 instances, containers, or serverless or Lambda functions on a single file system. So this is whether you're talking ECS, Amazon ECS, or Amazon EKS from a container perspective, or AWS Lambda as well. So a common question that we usually hear from customers is, why, for example, is EFS a great fit for some of these newer computing models, right? The first thing is containers and serverless functions are typically meant to be transient in nature. But what we're hearing from customers is a lot of you all are building stateful applications that require a persistent data store or a persistent storage system. And that's where EFS really comes into the picture because it provides highly available and durable storage for stateful applications. Another example is distributed applications like web serving, where you need state, machine learning inference, or CI/CD tools, for example, need a shared storage layer to operate data. And the third is if you look at data-intensive applications, so analytics applications, where data-intensive applications that require fast access to large volumes of data or to large data sets. And you need a file storage solution that can really act upon and make it easy for you to operate on those data sets really quickly. So let's talk about a real world example in which kind of all of these come together, right? So let's talk about machine learning at scale. So training machine learning models involves multiple steps. It gets more complex as you have more models and as the size of your models keeps increasing to like hundreds of gigs or sometimes terabytes in size. And so one application that really helps with this is Kubeflow. Kubeflow is an open source ML framework that takes advantage of native Kubernetes capabilities to deliver end-to-end workflows for data scientists, DevOps professionals, and researchers. The key advantage of Kubernetes is that it abstracts away the complexities of containerizing the code that you need to prepare, tune, and deploy these machine learning models. And it's used for a wide variety of use cases, such as financial modeling, natural language processing, computer vision, and so on. So let's talk about how EFS kind of fits into a simple Kubeflow architecture. So step one, obviously, you have EFS that you can use because it provides a configuration-free storage system to store your model artifacts and your ML models, so that both for training and inference. Next, because it's accessible from anywhere, you could use a Kubeflow architecture that's based on EC2, or typically, as we see, is the norm on EKS. The next thing is you can use any of the ML libraries that are typically available to any of you, MXNet, PyTorch, or TensorFlow, for example. And now the interesting part is because you're using EKS and EFS, you now have a fully serverless architecture, right, both on the compute side and the storage side. It's fully, so as you grow your training data, as you add more models, you really don't have to worry about your storage. As your compute, as you have, let's say, more CPUs or more GPUs accessing your architecture, you don't have to worry because EKS can really scale automatically as well. And then after the training is over, you can store your model artifacts on EFS, which you can then use for inference. So at a high level, this architecture uses EKS as a compute layer where you can create pods to perform ML training jobs, and then use EFS as the storage layer to store the training data sets. I don't show it here, but you could use Amazon ECR as the image repository that EKS could use for storing the machine learning container images as well. So if you think about it from a business application perspective, you now have a fully elastic machine learning model that's at scale and that works and that's available on demand. So a client application or a business application can simply make a request and get an ML-powered prediction on demand. It's fully serverless, it's highly available, and fully elastic as well. And if you look at it from an EFS perspective, not only do you have fully elastic storage for the vast amount or the size of for the number or the size of your machine learning models, but now depending on the scale of the compute that you have, with elastic throughput, you can now scale your performance as well without having to worry about storage provisioning and storage planning. So let's talk about a customer who's actually using EFS for some of their machine learning applications. So Asurion is a leading provider of device insurance, warranty, and support services, and their experts can really repair, replace, and resolve any tech issue. And because they're in this business, to ensure that their customers have a great experience when they call in and ask for customer support, Asurion wanted a way to measure the customer sentiment of their support calls. So there were a few things they were trying to optimize. One is because customer support volumes can vary over the course of a day, depending on the day, call duration times can vary. So they really wanted an elastic architecture that could scale up and down based on the amount of calls that they were getting, and they want to reduce their TCO as well. So they built an ML inference application using AWS Lambda and Amazon and EFS. And so what this did is the ML inference architecture automatically scales with the call volume. It reduces the operational overhead because it's completely serverless, both on Lambda, obviously, and EFS as well. And the benefits are that Asurion now has reduced operational overhead. It's reduced their total cost of ownership because they're only paying for what they use both on the compute side and on the storage side as well. So this is a great example of how a customer has really has a completely serverless and elastic machine learning inference application to solve a real business problem that they had. So now let's talk about the last thing that builders are looking for, which is you want the lowest storage cost for your application, but you really don't want to tinker with storage and figure out what the best way to derive that lowest storage cost for your application. And so EFS, there are no minimum commitments or storage fees with using EFS. You only pay for what you use, both from a storage perspective, as I talked about, and as well as from a performance perspective as well. EFS, from a storage data perspective, EFS provides low-cost, infrequent access storage, provides a low-cost, infrequent access storage class that's cost optimized for files that aren't accessed very frequently or accessed daily. So, for example, you can set policies to move data to this infrequent access storage class. And we do that by automatically tiering the data based on your application's access patterns. And how do we do that? So you can set a policy that says, okay, you have a range of options ranging from 7 days to 90 days, and you can say, okay, I think based on my application's access patterns, if a file isn't accessed for 14 days, move it to the lower cost infrequent access storage class. But then there are many applications where that have unpredictable access patterns, where you want the best cost per performance for your application. And so with EFS intelligent tiering, the SQL data is now moved over to the high-performant EFS standard storage class whenever the data is touched, so that you always get the lowest cost and highest performance for your workload automatically without you having to do anything to set that up. So, which means EFS can automatically reduce costs irrespective of what your application patterns are. So, now we are excited to extend this to 1 day, to an access frequency of 1 day. So what this means is, if you set a policy that says, make sure that my data, if isn't accessed within a single day, move it to the low cost and frequent access tier. So this is great for applications where you ingest your data on a daily basis, you do a bunch of data processing on it, and then you really don't want to act, and that your application really doesn't need to act on that data anymore, and you want to quickly and immediately move it to a low cost storage class, which is EFS infrequent access. So we're seeing a lot of customer interest, especially in analytics applications that typically process data on a daily basis. So with that, I will hand it over to Delvin to talk about a real customer use case that brings all of this together.
Let's dive into an actual customer example that brings it all together. So a lot of you here know about Johnson & Johnson, but for those of you that don't, J&J is a multinational pharmaceutical and consumer goods company. And we were working with Greg Rubin, an IT manager at J&J, and they needed a solution for sharing data across their growing team of data scientists so that they could collaborate on genomics, R&D, and drug discovery research. Their existing storage solution couldn't support the scale that they needed today, and it certainly couldn't support the scale that they predicted they might need in 5 years. On top of that, they had also grown tired of the operational burden that it took to operate and maintain and manage that storage. And so with EFS, they were able to deliver the simple, scalable shared storage they needed for their growing team and eliminate any of the operational burden of managing their existing solution. But why did EFS work? So first, because EFS was configuration free, it was dead simple for them to migrate their data from their existing storage solution. They didn't need to spend a bunch of time upfront qualifying the right configurations or settings that they would need to apply to EFS. They just spun up a file system and migrated their data over. Second, because EFS was fully elastic, they could confidently support the scale they needed today, as well as the scale they needed in the future. With EFS, they got simple shared storage that could scale up to petabytes on demand for their team of hundreds of data scientists. Because EFS was accessible from anywhere, it also meant that J&J could pick the right architecture for their data science application. And in this case, it meant that they could leverage a modern containerized architecture for their data and analytics on top of Amazon EKS. And lastly, because EFS is cost optimized without any effort, they were able to reduce their costs by 37% in just a few clicks. But don't take it from me, take it from Greg. With EFS, J&J were able to share data on a massive scale, increase innovation by accelerating analytics, and reduce costs by 37%. So I'll hand it over to Daryl to do a demo of one of the capabilities that we just talked about earlier.
Excellent. All right, thanks. Thanks, Delvin. So for this demo, you have an application that generates spiky, unpredictable workloads to a shared file system. Each process reads and writes 1 gigabyte of data. So to simulate your application, I'm going to use MPI and IOR, reading and writing to an EFS file system. I'm also going to be using 6 C7G 8XL instances. First, we're going to test your application's performance using a bursting throughput mode file system. So we're going to go ahead and go into the EFS console, look at the bursting throughput mode file system, and get the mount command. We're using EFS utils to mount these files, to mount all of our file systems on our EC2 instances. So I have all 6 EC2 instances loaded up right here. So we're going to mount the file system. I'm going to set my permissions for my demo. And I'm going to create a variable instance ID for my demo. All right, the first thing we're going to do is we're going to write 1 GB of data using a single thread on one instance. Over here, we're going to actually use nload to monitor the throughput of all the instances. We're only writing to instance number 1. So we see that we're getting, on average, around 40 megabytes per second from a single process, a single thread on a single instance. This is a new empty EFS bursting throughput mode file system. So we see that we were able to get about 41 megabytes per second from this process. Well, what if we increase the number of threads to 2? Now, as you can see, we're getting 60 to 70 megabytes per second of throughput. With a distributed file system like Amazon EFS, the more threads you have accessing the file system, the more throughput you're going to be able to drive. So we see here that with 2 threads, we were able to get an average of 65.85 megabytes per second of throughput. Well, let's keep going. We're going to use 4 threads. And we see that we hopped up to about 140 megabytes per second, but now it's settling in around 100 megabytes per second. So good performance, good enough for your application today. And here we averaged 105 megabytes per second. Well, let's keep going. Now we're going to use 8 threads. And we see that we're not seeing an increase in the amount of throughput this application is driving EFS. Why not? Well, the characteristics of a bursting throughput mode file system with no data in it is that we can burst up to 100 megabytes per second. If we had data in it, we could write to that file system at 50 megabytes per second per terabyte of data stored in the standard storage class file system. But because we have very little data in it right now, we're only using the bursting credits of the bursting throughput mode file system. So we're definitely, as we sort of scale this up, oh, and let's go back, and we average around 105 megabytes per second again from 8 threads. So if we go up to 16 threads, what do you expect? Still around 100 megabytes per second, because remember, that is the burst throughput limit of a practically empty bursting throughput mode EFS file system. So again, here, we were able to get 106 megabytes per second. Well, what if the application had to now read that data? What would it look like? Well, let's use 16 threads to read that data from a single instance. When we hop back, we see that we're getting much more than 100 megabytes per second. Why is that? Well, because for each write operation, we can actually do 3 read operations. So we can burst to 100 megabytes of write throughput or 300 megabytes of read throughput. So if we go back to our instance, we were able to get and drive 320, roughly, megabytes per second of read throughput to this bursting throughput mode file system. Well, what if we actually did that now against all of our EC2 instances? All 6. So let's go ahead and go back and restart the test by using a single thread. Now we see that all of the instances, instead of getting 40 megabytes per second, they need to balance that 100 megabytes per second across all connections, all 6 EC2 instances. So roughly, it's getting 17 megabytes per second. 17 times 6 is around 102 megabytes per second. So that's what we're going to be driving approximately the file system aggregate across all of our instances and all of our threads. So this should finish up in a few seconds. And then we'll see how does a read operation, yes, look when we're driving it from all 6 instances. All right, and you notice that they finished relatively at the same time because EFS tries to balance the throughput across all of its connections. If we hop back here, we'll see that on average, some of them are about 19 megabytes per second. So yeah, we were well above 102, maybe 105, 107 megabytes per second aggregate across all of the instances. Now, if we jump that up to 16 threads, what should we expect? We're already hitting that limit, so even if we had 16 threads driving write activity to this file system, we're only going to be able to drive 100 megabytes per second. So all of those threads, all of those instances are going to have to balance out, and together only get 100 megabytes, approximately 100 megabytes per second of write throughput to this file system. Now this is for a bursting throughput mode file system with very little data. With bursting throughput mode file systems, the throughput of the file system is based on the amount of storage you have in the file system. So as you add more and more storage to the standard storage class, you're going to be able to drive more throughput. So again, this should finish up here within the next few seconds. All right, now that write operation finished, let's go ahead and read. Oh, and let's just go back and say, yeah, we were roughly around 18 megabytes per second for all the threads across all of the instances. Now, if we did a read operation against these, what do you expect it to look like? Well, we're getting much more throughput. Now we're getting 50 megabytes per second. Why? 50 megabytes per second from each EC2 instance totals roughly 300 megabytes per second. Again, 3 times the write performance. So now, on aggregate, we're able to drive this file system. This application spikes up to 300 megabytes per second during its read operations. And again, it balances all of these threads and connections across all of the instances. And if we take a look at it, looks like we were getting around 58 megabytes per second across all. So actually getting even more than 3x the performance. So that was a bursting throughput mode file system. Now, how does your application perform with an elastic throughput mode file system? So first thing we're going to do is we're going to unmount our file system. We're going to go ahead and grab the mount command of our elastic throughput mode file system. And you notice the throughput mode here is elastic. So we'll grab the mount command. And we're going to mount it to all of these instances. We'll go ahead and run our permissions. And we'll just make sure that this is still there as well. OK. So let's go ahead and restart our test with a single thread, from a single instance, writing to that file system. So you've seen this performance before. a single instance, a single thread, a single process writing to this file system, we're getting roughly 40 megabytes per second, just like the bursting throughput mode file system. So really no difference because we have a single instance and a single thread. But we are going to see a difference, a change, as we start to scale up, and this application now becomes sort of a spiky, unpredictable workload. If we take a look at this, we were averaging around 39, 40 megabytes per second. So now if we scale that up to 2 threads, again, very similar to the bursting throughput mode file system, around 60, 70, maybe we're spiking into the 70 megabytes per second. So as we add more threads, we're going to be able to achieve more throughput for this file system. And here we were able to get around 67 megabytes per second. Now with 4 threads, remember before we were sort of hitting that 99, 100 megabytes per second? Well, now we're actually up to 120 megabytes per second throughput. So we're able to drive a lot more throughput because it's elastic. The EFS file system is giving your application, allowing it to have more throughput to the file system. So we were able to achieve 126 megabytes per second. Well, let's keep going. Your application now is driving 8 threads per on this instance. Now we're into the 200 megabytes per second. So we actually completed that in 4.5 seconds, 238 megabytes per second. And if we keep going up to 16, it's going to be even faster. Now we're spiking into the 330s to 340s. That completed in 3 seconds, and we averaged 339 megabytes per second. So again, we're able to elastically scale up that throughput for this file system. Now, if we wanted to read that file, what do we expect? Well, let's take a look at it. Now we're going to be reading. We're hitting 500 megabytes per second from this instance. An EC2 instance has a throughput limit of 500, roughly 500 megabytes per second, around 550 megabytes per second to an EFS file system. So we're hitting that limit on the EC2 instance. And we can see here that we hit 556 megabytes per second. We completed that in 1.93 seconds. Well, it worked great for a single instance. Now what happens if we actually scale this out? We have more instances and more threads. Okay, so let's go ahead and we're going to use a single thread writing across all 6 instances. What do we see? Well, each thread is getting around 40 megabytes per second. So before, remember, we were getting 40 megabytes per second from a single instance, but when we spread that across all 6, we had to ratchet that down and balance that 100 megabytes per second limit of that bursting throughput mode file system across all 6 instances. Now we don't have to worry about that. So we completed this in about 25 seconds, and each instance was getting around 40 megabytes per second. Let's go ahead and jump all the way up to 16 megabytes per second. Or sorry, 16 threads from all 6 instances. All the instances now jumped up to a little over 300 megabytes per second. So if we take a look at all of this, on average, it was 230, 228, 230, 230, 240, 230 megabytes per second across all. So now we're actually exceeding the throughput of that file system. This file system is able to write at 1 gigabyte per second. So we hit that limit. We hit that limit of our elastic file system using 6 instances and 16 threads on each instance. But now, if we did a read operation, what's this going to look like? Now, every instance is getting 500 megabytes per second. So now, each instance average 550, 490, 490, around 500 megabytes per second across all. So we're getting, again, the limit of that EFS file system, which is 3 gigabytes per second of read activity, or read performance to an elastic throughput mode file system. Thanks. So I'm going to go ahead and turn the time back over to Delwyn.
Great. Thanks, Earl. So elastic throughput, it's a super exciting capability. We're really happy to announce it, GAing here at reInvent. But in closing, just wanted to recap a little bit of what you heard today. So as you've heard, EFS is AWS's serverless elastic file system for builders. It's configuration free, which means you get highly available, highly durable storage without having to worry about any settings or knobs to configure. It's fully elastic, which means that you don't need to worry about provisioning resources or infrastructure to deliver the storage capacity that you need for your applications. And with our announcement of elastic throughput, you now no longer need to worry about provisioning infrastructure to deliver the performance that your applications need as well. It's accessible from anywhere, which means builders like yourselves can always choose the right architecture for your individual workload, whether it involves traditional server-based compute, containers, or serverless functions on AWS Lambda. And lastly, it's cost optimized without any effort, which means that you get pay for what you use storage with cost optimization features like EFS and frequent access and intelligent tiering built into its foundation. So put together, Amazon EFS delivers the just works storage solution for builders and data scientists like yourselves who are developing new cloud-native applications and workflows here at AWS. But before we go into the Q&A, just wanted to close with a few recommendations as you move forward. If you'd like to continue your AWS storage learning journey, we encourage you to do so at aws.training/storage, where you can build a learning plan with AWS Skill Builder, increase your knowledge with our ramp-up guides, or earn AWS storage badges to demonstrate that knowledge. And if you enjoyed today's session, we have more EFS here at reInvent this week. So on this slide, we highlight 5 other sessions that we have going on. We encourage you to attend, and we look forward to seeing you there. And to close, my colleagues and I will be handling Q&A. We'll stand on each end of the stage here, and we can take questions as needed. But thank you all for joining us. We're really excited to share with you what we have for EFS. Thank you.